Okay, so now let's begin the second half of the semester. Okay, so in my part, these are gonna be the topics that I have to cover for the rest of the semester. So basically, for the second half of this class, we will talk about it's gonna be eigenvalues and eigenvector. Okay. The tools and things that we'll talk about are going to be related to about eigen. The topics that you have to understand for the final, the first thing is the eigenvalue and eigenvector. What are they? How do we calculate them by hands? Second one is the power method. Power method. The third subject that I have to teach is called householder method. Householders method. And finally, we're going to talk about QR. Okay, so these are going to be the 4 topics that I have to cover for the rest of the semester. So let's begin with the first topic. So I think my plan is that I'm gonna do, one topic for one video. So basically you have pretty much 4 videos for the 4 topics, unless, I have to stop in the middle. So for some topics, you might have 2 videos or 3 videos divided into sections. We'll see if I get interrupted along the way. But if not, then I plan to have 4 videos for the 4 topics. So before we begin with the calculation of eigenvalues and eigenvector, let me first talk about homogeneous linear system of equations. Actually, for the term linear system of equations, we have learned about them pretty much before the midterm. So everything that we've learned tools to solve linear system of equations. But this is a particular, a specific type of linear system of equation. This is called homogeneous system. So what is it? What is the homogeneous system? So basically it's AX equals to 0. So rather than having the B to be anything like any vector, the right-hand side of the equation is all 0. So from this system of equations, this is actually a vector of 0, okay? So it's not going to be just the number 0, but it's the vector containing all the zeros, depending on the size of the A. For this system of equation, possible answers. So the answers to the above system of equation, the first thing is that, if X is all 0, then that means the above equation is true, right? This is so easy, and this we call it a trivial solution. It's a solution that's really easy to find, and you don't really care about it because, when X is all 0, then what's next? Nothing is interesting. The second question, the second question is the one that is more interesting. This is when X is not all 0. If we want a solution that X is not all 0, then what we need is that we need to have depth of A to be 0. So this is by definition. If you want to solve things for non-zero solution for the above system of equation, then you just need to solve for that A to be 0. And this is the solution that X is not all 0. We call it non-trivial solution. Okay. So let's see, for example, find the non-trivial solution for the above, for the following system of equations. So let's see, for example, we have the system where x1 plus 2, x2 minus x3 equals to 0. And the second question is minus 3x2 plus 3x3 equals to 0. In this case, we have 2 equations and 3 unknowns. If you write in terms of, ax equals to 0, in this case, your A is just the matrix containing 1, 2, minus 1, 0, minus 3, and 3, and 0, 0, 0. And your B matrix is just, the B vector, which is 0, 0, 0. And you also have x to be just x1, x2, and x3. Okay, so in this case, using backward substitution that we've learned before the midterm, we know that, from the last equation, you have 0x3 equals to 0. If you have the equation that looks like this, you can see that, hence x3 can be anything, right? x3 can be any real number. This is the symbol for the real number. So in this case, let's assume that x3 is just any a, which is a is any real number. So if x3 is any a, then moving up one equation above, you see that in the second equation, you have minus 3x2 plus 3x3 equals to 0. You plug in x3 equals to a, then you have minus 3x2 plus 3a equals to 0. So that means your x2 is just a, right? Solving this equation, you get x2 equals to a. Then again, you're moving up in the first equation. In the first equation, you have 1, 2, and minus 1. So it's 1x1 plus 2x2 minus x3 equals to 0. You plug in x2 equals to a, x3 equals to a. And so you have x1 plus 2a minus a equals to 0. That means your x1 is just minus a, right? So the solution to the above system of equation is that you have x equals to minus a, and a, or a times minus 1, 1, and 1, when a is any real number. Okay, so, from this solution, you can see that hence there are many possible x, right? Possible number of solutions, and that's fine. Okay, so for this, this is how, or the way that you pretty much use to solve the homogeneous system of equation. And this background is going to be used when you want to solve, for the eigenvalues and eigenvectors. So let's just move on to the topic of eigenvalues and eigenvectors. Okay, for the eigenvalues and eigenvectors, before we go into the calculation, I want to just give you some of the idea or understanding about what it is and how you want to try to understand it in your picture, in your big picture. So basically, eigenvalue is defined like that. So pretty much, you want to find any vector. So this is the vector. X is a vector, okay? Vector. So you want to find a vector that you can use it to multiply with the matrix A, okay? If that vector is multiplied by matrix A, and you get a linear transformation. So lambda is just any scalar. So, this is so amazing that, the vector x multiplied by a, and it's just the linear transformation of the vector x itself. If this is the case, then we say that if you can find lambda and x that makes the above equation true, then lambda is the eigenvalue and x is the eigenvector. Okay, so I'm just gonna give you some of the more pictures. So for example, if you have a matrix A1 that looks like that, 3, 2, 0, 1. So this is any matrix, okay? And you want to try to understand the eigenvalue and the eigenvector of this matrix. Let's assume that you also have x1 equals to 1 and 0. Okay. If this is, you want to see whether x1 is the eigenvector or not, then you multiply a1 with x1 and you get 3, 2, 0, 1, and you multiply it with 1 and 0. This is going to be 3 and 0. So this is just basically 3 times 1 and 0. So this is just 3x1. So you have ax1 and it finally equals to 3 times x1. So basically this means that 3 is actually one of the eigenvalues. So it's one of the eigenvalues and x1 is the eigenvector. Okay. To see it graphically, if you plot a graph, so this is just x and y axis. The reason that I do 2 by 2 is because I can plot, a 2 by 2 graph easily. So if you want to plot just x1, so let's see. So this is your x1, right? x1 is 1, 0. So this is 1. So this is basically vector x1. Okay, and after you multiply x1 with the a and you get 3, 0. So let's see, if you call this vector x2, so x2 is 3, 0. 3, 0 is just this line right here. So this is x2. Okay, so this is 3. So the green vector is x2. So if x2 is in the same direction as x1, this is called a linear transformation. So hence x2 is just the linear transformation of x1. Okay. And if x2 is just a linear transformation of x1, then x1 is the eigenvector. Okay. So this is just something that I want to give you the picture of how eigenvalue or eigenvector would look like in a 2-dimension space. But if you have a higher dimension, it's really difficult to draw a picture. But I think the idea is pretty much the same. Now, let's move on into the calculation of the eigenvalues and the eigenvector. Okay, calculating the eigenvalues and eigenvectors. Okay. I'm gonna start with a equals to 3 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, and 3. So this is just a 3 by 3 matrix. So we want to find, the eigenvalues and eigenvectors of A. First of all, the number of eigenvalues will be less than or equals to the dimension of A. So if A is a 3 by 3, the most number of eigenvalues that you can have is 3. Okay, there can be 1 eigenvalues, 2 eigenvalues, or 3 eigenvalues, depending on the eigenvalues that you can find. So let's just begin from the definition. We say that if x is the eigenvalue vector of A, then AX should equal to lambda x. So you move lambda x to the left hand side, it's AX minus lambda x equals to 0. You pull x out, and hence A is the matrix. Then pulling it out, you have to multiply lambda with the identity matrix I, and then you can just pull it out. Okay, so the matrix in the parentheses, this is actually any big matrix, right? So basically, if you call it, this is A hat, so you have A hat x equals to 0, and this is actually a homogeneous system of linear equation that we just talk about at the very beginning of the lecture. So if this is the case, then in order to solve for the x, to solve for non-zero x, we need det of A hat to be 0. Okay, and in order to solve for the det of the A hat, then we can use the definition of the cofactor and minor thing that we used to do previously when I review it before the midterm. So let's just do it again. So A minus lambda I. So this is actually 3 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, and 3, minus lambda I. Lambda times I is just lambda 0, 0. 0 lambda 0 0 0 lambda. You just subtract the first metric with the second matrix, and you get 3 minus lambda minus 1 0 minus 1 2 minus lambda minus 1 0 minus 1 3 minus lambda. And you want to find the det of A minus lambda I. And by definition, this is actually summation of j equals from 1 to 3, A1j, A1j. Note though that I selected the first row to be fixed, so you can select any row or any column, just by the definition of to find the determinant of the A minus lambda I. So this is the cofactor. Okay. All right, so let's just continue doing it. Since we select the first row, so we focus on this row, the summation is just 3 minus lambda. This is A11, small a, the letter A11, and times A11 plus the second one is minus 1, A12, and this is A12 plus 0 times A13. So this is just A13, the letter A. The letter A means the values in the matrix A, depending on the position, right? A11 is the first row, the first column, and so on and so forth. So let's just expand the cofactor. So this is 3 minus lambda minus 1 times the 1 plus 1 major 1, 1 minor 1 1 minus 1 times 1 plus 2 minus 1 2 plus 0. So we can just cut it out. Actually, minor 1 1 is just the det of the remaining matrix. So you cut one row and one column, and the remaining matrix is just that. So let me do it. So this is actually 3 minus lambda, and the det of the 2 by 2 matrix is just 2 minus lambda times 3 minus lambda minus 1 square. This is minus 1, this is minus 1, so it's just 1 plus the debt of the remaining one. So let me just cut the first row and the second column. This is going to be minus 1 times 3 minus lambda. So minus 1 times 3 minus lambda. Okay. All right, so let's just do the math here. I can just wrap things up. If you want to do it on your own, you can just pause here and then do it. But since I want to just skip it, so it's 18 minus 15 lambda plus 3 lambda square minus 3 minus 6 lambda plus 5 lambda square minus lambda cube plus lambda minus 3 plus lambda. Eventually, I have lambda minus lambda cube plus 8 lambda square minus 19 lambda plus 12 equals to 0. Okay. By solving this, you can just use any method to solve it, using the calculator or anything, but I'm not focusing on this that much. So I can have it to be classified into factors. So it's lambda minus 1 times lambda minus 3 times lambda minus 4. This is 0. So I get lambda equals to 1, 3, and 4. So basically, the 3 lambdas here that I found, these are the eigenvalues. So here from now, you know all the eigenvalues, but you can use these eigenvalues to solve for each eigenvector. In order to find the eigenvector, you have to plug in each eigenvalue and solve for each eigenvector. So one eigenvalue is going to get one eigenvector. So let's just begin with lambda equals to 1. When lambda equals to 1, then so from previously you have a minus lambda I times x equals to 0. So you plug in lambda equals to 1 here. So a minus I times x equals to 0. A minus lambda I times x. So a is just 3 minus 1, 0. Minus 1, 2, minus 1, 0, minus 1 and 3, minus 1, 0, 0, 0, 1, 0, 0, 0, 1, x equals to 0. And so eventually you're going to have 2 minus 1, 0, minus 1, 1, 1, minus 1, 0, minus 1 and 2 times x equals to 0. Again, you have a homogeneous system of equation. However, the last equation is not yet in the form of upper triangular. So change this, transform this matrix into the upper triangular form using just the normal Gaussian. So using the Gaussian one, then you know that, going back to the something in before the midterm, right? So m to 1 is just minus 1 over 2. M3, 1 is just 0. So, let's just do one round of the Gaussian. So for the Gaussian, if you guys remember, or you can go back and review it, it's 2 minus 1, 0. This is the pivot row, so we fix it. In the second row, this is minus 1 minus 1 over 2 times 2, which is going to be 0. 1 minus 1 over 2 times minus 1. And this I have a half. And the last one is 0 minus 1 over 2 times, minus 1. Minus 1 minus 1 over 2 times 0, and you just get minus 1. Okay, this is 0. This is going to be minus 1 minus 1 over 2 times minus 1. And here I have 0. And here, if I do the calculation, I have 2 minus 1 over 2 Oh, sorry, this is not 0. This is just -1. And 2 minus 1 over 2 times 0, and I get 2. So still I have to do the second round. In the second round, if I do the Gaussian, I have 2 minus 1, 0, 0 and a half, and this is -1. My M32, oops, sorry. So here, M32 equals to -1 divided by a half. So this is going to be -2. Okay. So they just do the, I just do the Gaussian one. Okay. Just the normal. I think I did something wrong here. Okay. Wrong color. Sorry. So this is 0, and this -1 minus 1 minus 2 times 1/2, and I have 0, and 2 minus 2 times -1, and -2 times -1, and I also have 0, hence x equal to 0. Okay, let me just write it nicely. So this is basically my output here after doing the Gaussian. 1/2 minus 1, 0, 0, x equal to 0. And again, this is the homogeneous system of equation. You just assume x3 equals to a. Using backwards substitution in equation number 2, you have 1/2 x2 minus 1 times a equals to 0. So x2 is just 2a, okay? And in equation number 1, you get 2x1 minus 1x2, 1 times x2, which is 2a, plus 0 times x3, which is a, equals to 0. So basically, you have x1 equals to a. So here, x is equals to a to a, and again, you pull a out, it's just 1 to 1. So this is your first eigenvector. And so this is the eigenvector for lambda equals to 1. So you just have to do the same thing. So do the same for lambda equal to 2 and 4, 2, right? Oh, 3, sorry. Where for lambda equals to 3 and 4. So you can do it in the, for practice. I'm not going to show you in this lecture. So next, we're going to move on into MATLAB to see how we can solve for the eigenvalues and eigenvectors using the built-in function in MATLAB. So I'm just gonna stop this video now, and we'll start the next video for the MATLAB session. Okay, now let me just pause it.